Well, we've just heard all about you, but I'd like to start with, just to set the scene, perhaps, is that for the person walking around out there on the streets in Hamburg, why should they care about this discovery?
Well, if we think about the process of disease, a doctor or a scientist might want to try to cure disease. But to do that, they have to understand how a cell works. It'd be like taking your car to the garage and the mechanic doesn't actually know how an engine works. How could they possibly repair it? And similarly, if we're going to cure disease, we have to understand how the cell works. And these discoveries were a basic way, one of the basic ways cells go about organizing themselves. And we can't understand how things go wrong unless we understand how they work correctly.
Well, I'd like to dig a little bit into cells, because we hear about them in society, we talk about them, but we don't often talk about the concept of a cell, these little things that make up our bodies, what they are and what they're doing. So just to set the context here, just tell us, what is a cell? What does it do?
Well, in the end, we're a collection of cells, with trillions of cells in our body that forms a collective that, like any collective, obey the rules that are set. The liver cells, and they should be liver, and the arm cells, and they should be arms. But they are their own living entity. They themselves have to make sure they take in enough stuff from the outside, make the right materials inside, divide when they should divide, die when they should die, and obey the rules. So that's what a cell does. Now, sometimes cells decide they don't want to obey the rules. We don't want to be part of this collective. And then that's when you get things like cancer. We're going to make our own little organism, and then you build some sort of tumor inside the body.
So, they sound, I think the concept of the inside of a cell, where it's a little molecular factory almost, you compared it to a village where there's all these, even inside the cell, there's lots of different things going on. They've got to coordinate. What sort of tasks are going on? What's going on inside a cell?
Well, like a village, for instance, you need energy. You have power stations, the mitochondria, or you have other types of machines that take sugar and make it into the energy stuff that we need. Or when we build our cells, we get bigger, we need more raw materials, so they bring in sugar and make raw materials out of them.
And so we're coming to the condensates and how they are where do they fit into the cell machinery? You've got this cell, it's busy, it's doing all these things. Where are the condensates in all of that? Where are they sitting and what are they doing? Well,
the way I like to describe it is that, in a society, we don't work as individuals, we work as groups. And there are types of groups that are together all the time, but there are kinds of dynamic groups that form, say like flash mobs. And the condensate is a dynamic process that forms just when the cell needs something, and it can be rapidly dissolved when it's not needed. There are other types of compartments, such as ones in membranes, which are much more stable, as an example, which might, like mitochondria, provide long-term energy usage.
So perhaps, an analogy in society is that, when it's time for school, the children all come to school and then they go away again. And
that's a very good example. Yeah, everyone, the children, the parents may be in the cafes, then the bell rings, all the children know it's time to run into the playground, and they run around. They're very dynamic. They know they can't leave the school ground, but they sort of form this liquid-like drop in a sense.
And so the discovery of these condensates, there's lots of popular, the ideas in films about how discoveries happen. But tell us a little bit about how this discovery was made. What was the moment when you thought, this is different?
Well, we were in Woods Hole, which is an oceanographic institute on the east coast of the United States. And there was a physiology course that goes back to 1880, I think. And every year you have to take 10 students for 2 weeks and teach them. And you're meant to do new discoveries, new experiments. And so one year we gave the students the task of filming these pea granules in high time and spatial resolution. And then the movies came up on the screen, and we stood in front of the screen, and someone said, I think it's my colleague Frank Ulica, it's a liquid. And suddenly we thought, wow, that changes the way we think about the cell. Just an immediate realization this was something we'd never seen before.
So what was the previous idea of what was in a cell? What was the idea changing from to understand it was a liquid?
It's like one of these things, I think it's more a question. Often discoveries are you find a question no one actually thought to ask before, which was you have this complex biochemistry in one place, millions of proteins somehow. Why do they stay in one place? So when we saw that, we understood a question that we never asked before that could be explained by this idea.
And one of the nice things about this a piece of research from the outside, I think, is that it's really important because it's physics as well as biology. So traditionally in school, you know, the biologists sit over there and they study plants and animals and cells, and the physicists are over there studying balls falling off slopes and things like that. I'm a physicist, I'm allowed to say that. You know, they're seen as very separate things, but this is down at the level of molecules then. These two things are coming together. How is that, I mean, how well are we making those connections?
You know, I think there's a real understanding that we have to bring these fields together to make progress. I mean, that's generally understood. The question is how you make it work. And I think that was my great bit of luck, you know, like as luck in all discoveries, that when I was in Heidelberg, there was a physicist on sabbatical, chap called Stan Leibler, and I suddenly understood, yeah, physics is an important way of thinking about how cells organize. And then I had a great bit of luck in Dresden, that the Max Planck, at the same time as building our institute, decided to build the physics of complex systems, and hired a colleague of ours, Frank Jülicher, and then together we started to explore how can we use physics to understand how this little C. elegans embryo started. And from that, working together for over 10 years, you know, we built the structures and thought processes to bring the two together.
So fundamentally down there at the level of molecules, you know, they're interacting with each other and they need physics rules as well as chemistry rules as well as the principles of biology. So you have to look at it all together.
Well, I think, you know, as you know, physicists are kind of an arrogant bunch, and they would say that actually, you know, it's all physics anyway, so there was no ever, all other fields were just sort of temporary, you know.
Well, let's not start the fight between the biologists and the physicists too soon. You can all do that in the drinks reception afterwards. So, and how easy is it to find out about what's happening inside a cell? You know, we hear about all these great discoveries, and sometimes on the television news, it's just as though somebody, you know, they just woke up one morning and happened to notice. How hard is it to get inside cells to watch the processes of life?
You know, it's an immensely complex process, and you can certainly say that it's advances in microscopy that have driven cell biology. Every time we make an advance, you know, there was original phase contrast microscopy going back a long time again, fluorescence, you know, all these different types of microscopy, one after another, many of which, you know, have led to Nobel Prizes. And all of those allow us to look deeper and better into the cell. So that's the basis of it all, and they take decades to, you know, to discover. So, and each time a new microscope comes in, what a cell biologist does, they look at their specimens again and say, could that help us? Right. You know, and then this case, it did, because it's a new type of microscope where we looked at it, and that gave us the resolution to look at the liquid-like state.
So you have a new pair of eyes.
Yeah, exactly, a new pair of eyes.
Things.
Yeah, it's true. It's like putting on glasses. Right. That's, yeah.
I think you're selling biology very well here. And how, you know, sometimes this is something scientists don't think about very much, that maybe you have, that how does it change the way you think about being human? Because, you know, we can all look in the mirror and we can see the view we're used to, or you can see, you know, you can imagine all the little cells and organs doing things. Does this change your, you know, when you, sometimes do you ever pick something up and wonder what's happening inside those cells? Do you ever think about that?
You know, not every day, but every so often you do step back when you think about something. You think, how can this possibly work? It's so awesomely complex. So the one I always like to use is that if we, you know, every cell has 5 billion proteins in it, roughly.
Can we just pause on that statement and say that again very slowly, because it's an incredible statement. Go on.
Yeah, every cell in our body has about 5 billion proteins, the population of the world.
That's in one cell?
One cell, and we have trillions of cells.
Okay, everyone just take a deep breath. Okay, so sorry, carry on. So, yeah.
Yes, so let's say you have 5 billion people in the world, and let's say a condensate has 1 million people, like the population of Hamburg. So you could say, oh, well, it's okay. I can imagine 1 million people coming together, they form a city, they do something, and they go away again. It'd be complex. But a cell is very different than that, because if you scale up proteins to be people, right? So you just say, let's take all the proteins and make them the size of people. And you ask, how dense would that be? we would all fit in Lake Como.
So this is a lot of people in a small
We'd
space.
be about this distance apart,
right.
swimming past each other about 3 square kilometers a second. And I remember the first time I did that calculation with some people in the lab thinking, that's just absolutely unbelievable. And looking at my cells suddenly differently and think, you know, in every one of those cells, that process is happening all the time. So there are those moments where you think, you know, this is it's just such an amazing process. It's a miracle, as I often like to describe, that could ever work. Yeah.
It is. I think whenever we see, you know, athletes going off the blocks in a race and we think they've got quick reactions, it's humbling to slow down and think about how much is going on. Well, so we're discussing here cells when they're working well. And of course, there are lots of reasons for doing basic research for curiosity and for our perspective. But really, the immediate applications of this are disease. And so in the years, you know, the first paper on this was published several years ago now. What doors have opened since then? Where does it look like this discovery might take us in terms of understanding disease?
You know, I think we didn't think about disease very much at all at the beginning. But then in 2015, you made this discovery that these liquids, when you made them in a test tube, we were looking at them, and they suddenly became these solids. And then we began, and we knew about solids from disease, because every neurodegenerative disease, a brain disease that goes wrong, or even the terrible disease when people hit the football too much, they have these protein aggregates. And so we thought, yeah, maybe that is the link for these diseases. And that was another extremely exciting moment. And then since then, we and others have begun to look for examples of, you know, where in disease, the condensates are in the wrong place. Just to give you an example, a cell has a nucleus, if we think back about in our biology, and a membrane. I think most of us remember that part. And if a protein gets stuck out in the cytoplasm and it's needed in the nucleus, the cell can't work properly. You know, and we've begun to discover more and more examples where the condensate is in the wrong place. And then the protein's in the wrong place, and then they can't work, right? So let's say, you know, you go to visit another town next door, and they build a wall around it, you can't get out, well, then you can't go back to your own town and bake some bread.
Right, so you're limited then, that all these very intricate processes are interdependent, and this one working depends on that one working, which depends on that one working.
Yes, in ways that are so complex we just don't understand most of them.
And how do you use, I mean, obviously these things are still being discovered, but might it be possible to have a medicine which alters the condensate? So how could we affect, I mean, it's one thing to watch it happening, but what could we do about it if it goes wrong?
Well, let's take the example of these liquid, like becoming more like solids. So in other words, a little bit like, you have a liquid maybe like honey, and then it becomes more and more so like a gel, like the jelly we have in England. I think luckily Germans don't know about it, but this disgusting jellies we had to eat as children. And then you could look for a medical...
It's great. We've got horrible jelly and we've got Brexit. It's wonderful in England. Carry on.
And so you could imagine the liquid-like drops turning into this more solid-like state. You could prevent that by adding a chemical. Right. And if you could slow that down, that might be a way to stop them becoming aberrant, as we call them, wrong condensates.
So it's very, I mean, there's all of this intricacy, and it's an amazing thing to think about going in and tweaking it. Yes. But this is what modern science allows.
Exactly.
If we understand it well enough, tweaking is a possibility.
Tweaking is the crucial thing, exactly, yes.
And what sort of things have to happen? Obviously, there's lots more research to come, but what sort of thing, what do we need to do next in order to realize that potential?
I think the thing about biology is just the unbelievable complexity. That's what puts so many people off. Because you make a discovery like liquid-like states, but then this incredible detail work has to begin, which you have to love. And the reason is that, 3 billion years ago, when the first primitive soup, from which life came, had some probably reasonably primitive physics, the type of physics that we learn about. But over 3 billion years, what has biology done to make that stable, work all the time? We live to 60 before most of us get diabetes. That means we've been eating sugar all the time, stressing our system, but the system's coping with that. And those are the rules, and that's incredibly complex. It's going to take decades to go through each one of these and really work out exactly, precisely how it works.
But if you don't start, you'll never get
exactly,
there.
You have to, yeah, exactly.
You have to get started.
Yeah.
And so is this, I mean, just in terms of, I know it's impossible to predict when things will happen, but how long do you think it will be before this might make a difference to therapies that people actually get?
Well, it's already made a difference in the following senses. If you take a drug and add it to a cell, you know, I think before these discoveries, people didn't really pay attention to the fact, where will that drug go in the cell? Will it go to a condensate or not? If your protein has gone wrong as in a condensate and your drug doesn't get there, what's the point? So just taking known drugs and looking at that, that's already people are thinking about that right away. So that's the first thing. And then I think, you know, the drug programs and cells that start from the beginning, they take a decade or something to get to work. But there are many biotech companies around the world, but also pharma companies beginning to use these ideas to think about how to make their drugs better.
And what does it, I mean, when you first published the paper, was the reaction positive immediately, or did it take a little while for everyone to realize how important it was?
You know, it was a sideshow. You go to the fair and you've got the main Ferris wheel and then it's some little stand on the outside. I mean, I think people, including us, understood it was a cool discovery, but we didn't understand in any way how broad the implications would be. So I think people thought, oh, it's a cool discovery. And then with time, as we spent more and more time on it, more and more demonstration in other systems, people began to understand that it might have, you know, more general application.
And what does it feel like to have this idea that you see something in a microscope with your team, and then you watch this idea roll out into the world, and there are other people writing papers based on this idea, and you've never met them, you've never seen their labs, you've no idea who they are, and how does that you know, you're just this idea, this baby just rolls off into the world, how does that feel?
Wonderful. You know, that is the hope of every scientist, I think, you know, that you develop some idea that changes the way people look at what they're doing in the cells. They have to take it and take it further, you know, because all we are as scientists in the end is we make discoveries and we hold the scientific method in trust for the next generation. We train our students, we train our postdocs. You know, I've had 50 scientists go through my lab, probably, and I sort of train them, and then, and that's, you know, so that's the wonderful feeling, because you know that your ideas have been carried forward into the community.
Passed on. Well, let's talk about your team and your lab, because, and actually back to the beginning, because I think for anyone, you know, I know you were talking to news reporters this morning, for anyone who sees that scientist on the news, and you're wearing a suit and you're in a posh hall and you're getting an award, and it feels a long way from everyday life in that context. When you were a kid, did you want to be a footballer, or did you want to be a fireman, or did you always want to be a scientist? How did you get started on all of this?
No, actually, I want to be a bicycle mechanic.
Right.
So I was never very good at school. You know, I did try hard because I knew it's important for my parents, but I just didn't do well in exams. You know, I wasn't lazy. And it didn't even occur to me to go to university at the beginning because I didn't do well enough in my A-levels, so I became a lab technician because my friend Raf and I wanted to build a bike shop.
Right.
He was a jazz bass guitarist, and I went to work in the lab. And he's still playing jazz bass, and I'm still in the lab. Because once I got there, I understood there was an aspect of what I was really good at, which was very good with my hands, you know, and so I could make experiments work well. And then I got more and more into it, and then I went to university, and then all these courses on these incredible molecular machines inside cells, and I was thinking, oh, I want to work on these machines. And then I got started, and then the rest is history, really. Just stuck with it, and then ended up where I am here.
So not a bicycle mechanic, but a cell mechanic.
Cell mechanic, exactly. Exactly.
And what drives you? You know, so I think a lot of scientists, it's easy. You get up in the morning. A lot of people, you know, you just sort of do your job because that's what's in front of you. What drives you in how you choose the scientific questions you choose to work on, or you know, those directions? Is it just curiosity? Is it because it could help people? Is it because science is fun? What gets you out of bed in the mornings?
You know, I mean, the basis of being a good scientist is curiosity, and I always say that to people. You know, you've got to get up every morning and want to understand how it works. I mean, without that, you can't be a scientist. But there's another thing, I think, which is important in driving discovery, is discontent. right? You have to have this constant discontent with what you've done to make you do the next thing. My father used to call it divine discontent, is that, it's, and I think that's a crucial thing. You do something, instead of sitting on your laurels thinking, oh, that was great, then you think, that was okay, but so-and-so, I've got to do more. And those two things, I think, are what keep you going as a scientist.
I think you probably have to come, it sounds not unhealthy, but something you have to keep an eye on.
Yeah.
Are you a perfectionist, or are you just...
No, I'm not really a perfectionist. I just, I get bored quickly. So therefore, if I'm doing something for a while, and then nothing new's happening, I get bored and I want to move to the next thing, and so that's been a crucial part of keeping me going through all the long period of being a scientist, because it is a long-term process, making discoveries.
Are you a patient man?
I am patient, yes. Relatively patient, yeah. I used to ask my children. I would ask Luke what he thinks.
And so let's come to teamwork then, because, it is true, you are being honoured for this award, but of course there is a team around you, there's a team in the past. Tell us a little bit about the teamwork you do and who's on that team.
Yeah, I think science is a curious business, because if you make a discovery like we did in 2009, you have the time leading up to it, which later, and you've got the time afterwards where you actually show that it was important. And you can't be a scientist without the teamwork that goes behind it. If you think in my case, of course, there's the group, right, the scientists, the students and postdocs, over 30 years, 50 of them have gone through my lab. Without them, they did all the work. It's impossible. But then, being a scientist, this discovery, you could say, took 30 years to where we are today, and that requires long-term support. And so, for instance, in my case, a crucial part of the teamwork was the founding directors. It was Ivan Baines, Joe Howard, Wieland Huttner, Kai Siemens, Marina Zerial, all of us who in 1996 thought, let's go east. Let's go to Dresden, start a new Max Planck Institute. So that teamwork over so long provides a stability that allows you to do these discoveries, every day. And then you have your collaborators, people you've worked with over the years. Stefan Grill, who's in the audience, a crucial part of developing the physics, Simon Alberti, others. And so I like to describe it a little bit like a universe. You've got the sun, which is your stable core, but there's a whole set of planets have to revolve around it, your collaborators, your groups, other people, to make that system. You have to be stable. And then, of course, the family structure, right? Without a family structure over the time, you can't be stable. In my case, my wife, Suzanne Eaton, I'd like to dedicate this to her. We lost her in a appalling tragedy in 2009, and without her love, affection, and intelligence, none of this would have been possible. And these are the things that all have to fit together over a long period to be a scientist. It was like Peter Medawar said in one of his books, an artist like Van Gogh can cut off his ear, and everyone goes, wow, cut off his ear, that's a great thing. But a scientist cut off their ear, they would lose their job the next day. So, so for us, it's stability, quiet, just, So.
But it's important, is it, to recognize that science is a human endeavor, and for all we hold up the ideals of science as being objective and not influenced by, our personal preferences, the best thing about it is that it's human, that we are humans working on teams with other humans, and we are enjoying the best, the curiosity. These are very human things, aren't they?
It's the most human of all occupations, being a scientist, because there's no obvious, like you don't make money like in a company. There's not, what is the actual output? And so in the end, what the output is, the way people work together in these teams and enjoy the teamwork, I would say. That's what people love about working in a lab often, is the constant teamwork you do over long periods. And the way that team works is fundamental for discovery. If it doesn't work, you don't make discoveries. And so a huge amount of the work as an institute director group is about making people work well together and giving them conditions to feel happy. And because science takes such a long time, discoveries, 30 years, the long-term trust. If I work, I will be supported over a long period of time. And that, of course, is a great thing about the Max Planck Society, for which, these discoveries wouldn't have happened, because it's the last organization left, I know, in the world that says, 36, Tony, here's money to retire, make some discoveries. And those...
So you were 36 years old when they put that trust in you.
Yeah, they did, exactly. You know, and those are probably special times after the wall came down. You know, who were the crazy people who would go east at the time? And you know, that allows you then to do long-term discoveries. You have the trust. If it doesn't work, the money's still there.
To have faith in the science. Yeah. Well, you have some quite perhaps unorthodox members of your team, your dogs,
yes.
who come with you quite a lot. So tell us a little bit about your dogs.
Well, they're two whippets, racing dogs, rabbit hunters, in theory, although we never let them hunt a rabbit. But there was an outbreak of rabbits recently in Dresden that made life extremely complicated. Because, and yeah, that's, so they go with me everywhere. You know, the whippets, as my father used to say, they're lovely animals, but not dogs. You know, if you have a Labrador and you get home, it's always happy. But these dogs, they mirror your emotions, so it's even worse. You get home, you've had a bad day, they're suddenly unhappy, so then you have to make them happy. But it's, yeah.
So you have to face up to yourself that day.
Yeah, they make you face up to yourself every day, exactly. Yeah.
And do they stop you working all the time, or you know, do you sort of find time away from the lab? What do you do? Do you relax? It's always a difficult question to ask a very accomplished scientist because many of them don't admit to relaxation. Do you relax?
Actually, I mean, I do. In fact, I'm known for relaxing. My nickname in the cycling club in Dresden is Kaffee Pause Hyman, because because every time we go somewhere, I want to stop for a coffee. So I do a lot of cycling. That's how I relax my. And I also play the flute, and so that was wonderful to listen to such a young, accomplished flautist. I'll never be as good as him, but it's still something which relaxes me and switches your mind off. You know, so music and exercise provide these two sort of alternative ways for your brain to work.
I often wish, so my students at University College London, they sometimes say, oh, I'm too busy doing science and engineering to do sport and music. And I want to say to them exactly that no, you need to be a good scientist, you need to allow your mind space. It's like having space, isn't it, to let your mind do something else. I
think that's a good way to say it. I mean, I often say also to my students is that, you know, the discoveries don't come from your thinking process, they come from the subconscious. The brain puts it all together, but how can the brain put it together unless it has the facts? That's the fuel of the brain. You have to fill it with facts and then stop. Like sleep over it, the classic thing we know, you know, or the phrase, the morning is clever in the evening, that's a German phrase also. And, you know, and that's why I stop.
So some condensates have to have some work to do.
Exactly, they can go in, exactly.
And so then, you know, looking to the future, what are you most excited about, either professionally or personally? What are the big things that you're excited about coming down the line?
You know, at a sort of professional level, I'm, you know, still super excited about finding out how condensates are controlled. You know, that is wonderful, new people coming in every day. You know, I'm excited. I think the older one gets, the more excited one becomes about drug discovery and making sure that the discoveries we made have some application in medicine. And then otherwise, you know, it's the great thing about a scientist because you never know. You come in every day and a student or a postdoc comes to you and says, look at this. And you go, oh, wow, maybe I need to work on that, just like we did in 2009. So.
Well, that is a beautiful way to finish. Please, everyone, join me in congratulating Dr. Anthony Hyman.